Hello, everyone. It's time to do a little more organic chemistry. We are starting Unit 4. Woo! This is our last full unit of the second semester of organic chemistry. There is a Unit 5, but it's much shorter than Unit 4. So I feel like this is the last big chunk of organic chemistry we need to go over in order to complete the whole course. How about that? Very cool. Okay, so Unit 4, Part 1. Okay, so we had a little bit of good news there. We're almost done with organic chemistry, and a little bit of bad news. Hey, these reactions are weird. Well, I remember being a student and looking at these for the first time, and it's like, what the heck are this? It's very strange. To get through it, what you have to do is just kind of relate it to things that you're more familiar and more comfortable with. So I'm going to do that from time to time. As we start looking at these reactions, I'll point out the similarities to something that's easier to understand. The other thing too is that the molecules we're using, at least for the first half of this unit, they're big. There's a lot going on. And so you really need to know your functional groups and just kind of parse out the molecule, just kind of break it down and say, okay, it's a big molecule, but let's just look at it in pieces. Look at the functional groups, and then we can just focus on the one aspect of the molecule that's doing the reaction. And then we can just treat the rest of the big molecule as just decorations, just stuff that just goes along for the ride. Cool. Okay, let's jump right in. Let's review a couple things. Organic chemistry, actually all chemistry kind of builds on prior knowledge. We keep stacking on top of old knowledge, and that's what we're doing here. So if we look at the name of this section, these are going to be alkylation of enolate ions, or the more proper term is carbonyl alpha-Substitution reactions. So let's review what alpha stands for. That's the old Greek labeling system before IUPAC came along and numbered things a little more properly and a little bit more meaningfully. The old chemists were like, hey, where's this group relative to the most important group? So relative to the ketone, that would be the most important group in this molecule. Hey, is there a decoration, a halide, a double bond? Is there something else in the molecule? Where is it? Well, if it starts right next door to that ketone, that's the alpha carbon. And if it's farther away, they use the Greek letters to represent the position of the extra group, the decoration. So over here on the beta carbon, right? So most important group is ketone, not alcohol. The more pi bonds or the more oxygen atoms, the more important the functional group becomes. Ketone outranks the alcohol. So ketone's most important. Hey, where's the alcohol relative to that ketone? Well, it's not next door, it's 2 carbons away on the beta carbon. So they call this a beta hydroxy ketone, right? The alcohol group with the prefix name would be hydroxy. And then on carbon, the carbons right next door to the ketone on alpha and beta, you could have a degree of unsaturation, an alkene, but we call this molecule an alpha beta unsaturated ketone. Okay, so that's the first thing we have to remember, the alpha carbon. And actually, that's going to be the one to focus on. Just keep watching the alpha carbon. That's where the reaction is going to take place. And the rest of the molecule will be decoration for the first half of the mechanism, and then the decorations will participate. And that's when it's really important to review your older chemistry, because it's just going to be a review of things we've already seen. Okay, are you comfortable with alpha carbons? Yeah, let's move on to the next idea. If you have a carbonyl group, we're talking aldehydes and ketones. Carbonyl is C double bond O, but C double bond O is also found in the esters, carboxylic acids. Let's do the list, right? Carboxylic acids, and there's acid chlorides, anhydrides, esters, and amides. Prior knowledge, building off old stuff. Yeah, so relative to the C double bond O and all 7 of those functional groups, aldehydes, ketones, carboxylic acids, acid chlorides, that's 4, anhydrides 5, esters 6, amide 7. Yeah, all of those next door to that C double bond O group. If there's a hydrogen there, hey, new idea, it's weakly acidic. So that's what brings us in the unit form. So here we have an aldehyde, and here's the alpha carbon right next door. So one of these are alpha hydrogens, and these are beta over here, and these are gamma. Who cares about those? It's the alpha hydrogen that's weakly acidic. So it's kind of rare. It's a rare event, but sometimes a hydrogen falls off, right? Not so rare with HCl. That falls off all the time, right? HCl is a strong acid, donates hydrogen ions all the time, completely, not in equilibrium. Strong acid. Well, this is a weak acid, and it's very, very weak. The hydrogen comes off. So why is nature allowing that? Because what are you doing, nature? You're creating a carbanion. A carbon that has to stabilize a lone pair with a negative charge. And carbon is not electronegative. It doesn't want to do this. Well, it gets a help from resonance. The pi bond of the carbonyl group right next door to this lone pair, that's conjugated. And so the lone pair can create a double bond, and the pi bond, the oxygen, can kind of be pumped up. You can bump up the pi bond and give the oxygen a third lone pair. And now oxygen is more electronegative than carbon, and it can stabilize the negative charge. There you go. And so, kind of cool phenomenon, these hydrogen atoms are weakly acidic. Let's get a feel for how weak is weak, right? Because we know HCl is a strong acid. This aldehyde, how weak is it of an acid? Well, it turns out really weak. So here's a table of pKa's. Attention chem majors. In graduate school, I had to memorize the list. So if you want a head start, you can. Hey, the rest of the class, I'm not having you memorize pKa's. I want you to just get a feel for the trend, right? So what you need to know is that if you have a carboxylic carboxylic acid, then yeah, that's a fairly relatively strong acid relative to other organic compounds. HCl is a strong acid from GenChem. I think it had like a negative pK value. 7 jumps to mind, but I'm not going to put it on the screen because I can't remember exactly. Back in general chemistry, we said carboxylic acids were weak acids. And that's still true. It's a relative rating. If you're comparing HCl versus a carboxylic acid, yeah, carboxylic acids are weak. But if you're ranking carboxylic acid versus an aldehyde, okay, aldehydes have a pK value of 17. Carboxylic acids have a pK of 5. And do you remember pH? When if you have a low pH, like a 1 or a 2, and you have a higher pH, a 3 or a 4, the lower the pH, the stronger the acid. Same trend for pK. The lower the pK value, the stronger the acid. So 17 is not a very good acid. Now let's compare it to something a little more familiar. What if we have water? H2O. I had to go and look it up. It's 15.7 something. I don't remember. 4. There it is. Okay, so if you have pure water, right, there's an equilibrium water can do to create the to create the hydrogen ion and hydroxide ion. And it turns out in water, this is your strongest base and that's your strongest acid that's possible. And so if you have other functional groups that have larger pKs, generally they're not acids in water. Because if, for example, the alcohol group says, hey, I want to be an acid too. Well, you just created a base that's stronger than hydroxide ion. And so if you're trying to do this on water, this base is going to go attack water, it's a solvent, and take its hydrogen back and reform the alcohol. So in water, we generally think of alcohols as not acids. Oh, why is this base stronger than that base? Oh my goodness. Have we worn out that video yet? Is YouTube blown up and said, stop playing the order of basicity video? Yeah. Well, keep trying to break YouTube. Keep going back and looking at that until you know those concepts, right? So if we need to rank a base, like I'm asking you to do here, is this stronger or is this stronger? You got to rank it. First thing you look at is electronegativity. Okay, who's bearing the negative charge? Oxygen and oxygen. So they're tied. If you had carbon, that's going to lose and make a stronger base. If there's resonance, that weakens the base and stabilizes the base. Well, neither one of these two is resonance stabilized. And then the third thing is Ortho Para versus meta-directing groups. If the negatively charged atom has a meta-directing group, well, meta-directors deactivated benzene, they also deactivate bases. So what's a methyl group? Well, back in benzene chemistry, a methyl group was a weak activator. Well, here, methyl is activating the negatively charged oxygen. It's making a stronger base. And that's how we know the methoxide ion is a stronger base than hydroxide. We were talking about aldehydes some time ago. Sorry, I got a little distracted, but acid-base chemistry is fundamental in organic chemistry. You gotta have a clear concept of that. Turns out the aldehyde is an even weaker acid than alcohol, than water, than definitely carboxylic acid with a pK value of 17. In fact, when I was a student and I looked at an aldehyde, I thought this is the hydrogen that was supposed to fall off. No, it's one of these other three. And the reason for that is the second trend, resonance structures. So I made this mistake as a student and said, hey, how about we have the aldehyde's hydrogen fall off? And then I incorrectly said, well, maybe this lone pair can fall up here and make a triple bond to the oxygen. And then nature says, no, that's because if you added another pi bond here, you know, the lone pair becomes a pi bond. Now you have 10 electrons around oxygen and it can't violate the octet rule. So no, that's not, this hydrogen is not the one that's acidic. Instead, it's one of these three over here. So CH2, C double bond OH, with a lone pair on this carbon, right? It had three hydrogens. One of the hydrogens came off as a proton, a naked hydrogen atom, no electrons in H+, it's just a proton. And then what became of the bonding electrons that held this hydrogen to the carbon, it's now a lone pair, negatively charged. And now this lone pair can fall across the two carbons. And I don't want to use equilibrium arrows because we're not drawing an equilibrium, we're drawing a resonance structure. You can make a double bond to that carbon. And now I can't keep this double bond to the oxygen, it becomes a single bond and negatively charged. We bump up the pi bond. And we have resonance structures, and the more electronegative atom is holding or trying to stabilize the negative charge. What else do we need to know? Well, what about carboxylic? We did carboxylic acids. This hydrogen is the more acidic one. This one could fall off and do resonance, but in one of those resonance structures, the carbon has a negative charge. So nature says, no, 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 just let this hydrogen fall off. So the oxygen in those resonance structures, the oxygen atom always holds a negative charge, much better than carbon holding on to a negative charge. But in ester, you can get the alpha hydrogen to fall off and get resonance structures over here. You can also do it the nitrile group. Okay, now your pK value is even getting higher, which means it's even a weaker acid. Aldehydes and ketones are much more likely to donate their hydrogens, alpha hydrogens, than esters and nitriles, but they still can do it. Amides can do it too, but the pK now is up to 30. Ouch. What about just a regular amine? Why is this even here? There's no double bond O. Well, just to kind of give us a, point of reference, when we looked at the order of basicity, we looked at electronegativity. That was the first trend. Something special about sp hybridized carbon that can stabilize the negative charge. Triple bonds are less basic than nitrogen with a negative charge. I know, that's weird. Okay, so if nitrogen has a negative charge, we consider that a very strong base. Carbon negative charge should be a much, much stronger base. But nitrogen, pretty strong base, right? We've been using NaNH2 all over the place to make strong bases. We'll see in Unit 4 that we're going to use nitrogen as a strong base a lot, but not in this form, because this powerful base is also somewhat nucleophilic. Remember nucleophiles? We talked about nucleophiles in SN2 reactions, the N, nucleophilic. So if you had ammonia and a primary halide or a methyl halide, maybe I'll draw the bond to the bromine. Remember the SN2 reaction? Nice short mechanism, 2 curved arrows, lone pair on the nucleophile, ammonia in this case, hits the carbon and bumps out the leaving group. And in this SN2 reaction, then you will make an amine. And a halide ion comes off. If you have this molecule, this is a much stronger base than ammonia. So it's mainly a base to do acid-base chemistry. However, the nitrogen has 2 lone pairs. It can still be nucleophilic in an SN2 reaction. So in Unit 4, we want to use this base to create some of we want to help the alpha hydrogen come off. So we need a powerful base. Kind of already mentioned the hydroxide ion is not very basic. You know, by comparison, the pKa of water is 17, that's 15.74, whereas the alpha hydrogen of the aldehyde 17. So back up, Dennis. The trend with pKa is the smaller the number. So if I compare 15 versus 17, the smaller number is a stronger acid. So water is more acidic than the aldehyde. But what can you say about the conjugate bases? So if this aldehyde releases H plus as an acid, it'll create this base, the conjugate base. And if water acts as an acid, it'll create this base, the conjugate base, hydroxide. So who's more basic, hydroxide or the conjugate base of the aldehyde? Well, the pKa values can help us. We just said that water is a stronger acid, so everything's backwards. If you look at the base, the other one is a stronger base. Or maybe you learned it this way. If water is a stronger acid, its conjugate base must be the weaker base. And that's true, which means this is a stronger base. And in other words, hydroxide ion is not a strong enough base to pull this hydrogen off. You need a stronger one, like, well, go to a higher or stronger base. The triple bond, yeah, but you have to make that. So just go and grab this sodium amide. That's a stronger base. They can remove the alpha hydrogens. However, this molecule suffers from a little SN2 nucleophilic attack. So what if we bulk it up? Because SN2 doesn't like crowding. So let's bulk up the molecule with the lone pair with some isopropyl groups. That's what this I means. This is isopropyl and then 3 carbons, isopropyl. Yeah, so we're going to start with this molecule. And if we remove the hydrogen, well, it had 1 lone pair. If you remove the hydrogen, now it has 2. And then it's commercially available as a lithium salt. So this molecule is going to be lithium diisopropyl amide. All one word, sorry. Diisopropyl amide, one word. That's going to be one of our common bases, because when the amine has a pK of 36, That makes it the weakest acid. The conjugate base, though, will be the strongest on this list. Do I need to say anything else? I don't think so. It's probably too much. Sorry, I got hung up there. But if we can get a good understanding of the acid-base chemistry, that'll help us get through Unit 4. Okay, a little bit more about the alpha hydrogen being weakly acidic. This explains keto-enol tautomerization. So we'll go to tautomerization in a minute. That should be familiar to you. We've seen it, I think, 3 times in the past. We'll review that a little bit in a minute. Let's just look at ketones and enols here for a second. So because that the alpha hydrogen is weakly acidic, one of these 3 hydrogens can come off. And then we can create a lone pair on the carbon, and then we can get resonance that puts a double bond here. And then the hydrogen we pulled off can be placed back on the oxygen. We'll break down that mechanism in a second. All I'm saying is that these are isomers, not resonance structures, because you're moving atoms. In a resonance structure, you can only move electrons. All the atoms have to stay put. But you can hopefully clearly see that there were 3 hydrogens here. Now there's only 2. There's no hydrogen up here. Hey, now there is. A hydrogen atom moved, makes it an isomer. And what the heck is this thing? Well, it's got an alkene, and it's got an alcohol. So we'll take the ene and the ol, and we call it an enol. And most of the time, so here's what you need to know. Well, hopefully you remember ketones and enols, and if not, you need to know that. And then the next thing you need to know is that, generally speaking, the keto form is the more stable form. There's something special about C-double bond O that's just really stabilizing. I remember carbon dioxide is a very stable molecule, and it has 2 of these C-double bond O groups. So that kind of helps me remember. Oh yes, nature kind of likes carbon-oxygen double bonds. It's a very stable bond, double bond. So that's the driving force here between acetone and the enol form, less than 0.1% impure acetone. Doesn't really like to form this, but it's not 0. It does happen. But the equilibrium largely favors the ketone form. Wait, what about this molecule? How come it's only 24%? And wait, what about this ketone? It's less than 0.1%. Well, even though the C-double bond O group is one of nature's little favorites, it's nice and stable, she has some other favorites too. Let's go down to here. Why is this almost 100% enol? Benzene, right? Back in unit 1, we talked about aromatic compounds. One of nature's favorite functional groups, really, really stable. How do we know it's aromatic, right? We have to check and see if it has a ring, see if it's flat or planar, see if there's conjugated, extended conjugation. Oh my goodness, it's been too long. And we have to check for the Huckel number. Yeah, okay, so this is aromatic, very stable. Nature says, oh, the heck with the keto form. Let's go to the enol form so we can be aromatic. Is this aromatic? No, right here, we don't have extended conjugation, right? This is sp3. There's 2 hydrogens here. But it's an alpha hydrogen relative to this ketone. And it's weakly acidic, so the hydrogen can fall off and go up onto the oxygen. And hey, nature says, yeah, let's shift the equilibrium to this side so we can get an aromatic compound. And that's what I think she's doing here. First of all, there's hydrogen bonding. So when you isomerize, make the isomer, go from the keto form to the enol form, you get an OH group. There's the OH group. And then over here on the other ketone, there's a lone pair. And so just like water does hydrogen bonding, right? The lone pair of one water molecule can stick to the hydrogen of the next water molecule. That's a hydrogen bond. We get an internal hydrogen bond. Lone pair on the ketone get hydrogen bond to the enol of the other functional group. So there's an internal hydrogen bond, more bonds, more stable. That's driving this up from 0.1% to higher. But let me ask you this, is this aromatic? Well, the big question for me is, does it have a ring? Is that really a bond? Probably not. So the answer, the literal answer is no, this is not aromatic. But it's pretty darn close. So that might be another driving force, right? So if the hydrogen bond counts as a covalent bond, I don't think it does. But if it did, yeah, we have a ring of 6 atoms. Is it planar? Well, this oxygen's sp2, so is this carbon, that carbon. This oxygen has 2 lone pairs. It's sp3, but maybe nature can rehybridize that to be sp2. Ooh, but what about hydrogen? It's just 1s. It's not hybridized at all. Yeah, but that's a sphere. That's kind of weird to think about. Sphere doesn't have an angle. This bond angle could be in the same plane. So it might be planar. Does it have extended conjugation? Well, is everybody sp2 hybridized? Not the hydrogen. So no on that. Huckel number, well, I got 1 pi bond, 2nd pi bond, and if this rehybridized, hey, we actually do have a Huckel number of 6 pi electrons. So it's pretty darn close to being aromatic. I think it's the internal hydrogen bond that's really bumping this up, favoring the enol form. But a little review of aromaticity there, huh? Oh yeah, and keep this in mind. All these ketos and enols are not resonance structures. We're moving a hydrogen, right? No H here, and now there is. They're isomers. So watch your arrows. These are equilibrium arrows. The single line with double head, that's a resonance arrow. So be careful with your usage of the arrows. Okay, where do keto-enos show up? Okay, I counted 3 places when we went over the mercury catalyzed hydration of alkynes. So if you have a triple bond and we mix in some mercury sulfate, I can't remember, it was sulfuric acid and then water, or did I put this water on top? Whatever. There's this reagent. During the mechanism, you actually created an enol, put in parentheses because that's not the final product, and then it tautomerized to the ketone. Hydroboration, oxidation, alkynes, right? So we actually took the alkyne and mixed in our borane with THF and used hydrogen peroxide and base. And we got the other regioisomer. This one with mercury does Markovnikov addition. The carbon with more hydrogens gets a hydrogen. But hydroboration oxidation does anti-Markovnikov addition. So we created this enol, which then tautomerized to the aldehyde. And then finally, a Claisen rearrangement. That wasn't too long ago. If we had a phenyl allyl, so allyl has 3 L's, so 3 carbons, 1, 2, 3, and then make it attached to an ether, and on this side, put a benzene ring. And then we heat this up, and it rearranges. More review, right? Did I draw that right? 1, 2, 3 carbons, yes. Close up the gap. Look like a Diels-Alder reaction, 3 arrows, 3 bonds moving. Whoops, watch the arrows. This bond left, this one became a double bond. Oxygen's up there. So I'll start here, oxygen, no bond, double bond, single bond, and then a single bond closes the gap. Connects it to the benzene ring. This pi bond left to make a double bond, and then those 2 stay put. Put that in parentheses because that's our intermediate. Nature says, wait, where'd my benzene ring go? Yeah, here's the keto form. There's an alpha hydrogen right here. Remove this hydrogen because this is not aromatic. This carbon is sp3. And then you can do the keto-enol Tautomerization, get that aromatic ring back, and you create a phenol group. There we go. All right, 3 times we saw keto-enol Tautomerizations. Let's explain the mechanism for it. It's pretty straightforward. So all 3 of those cases, wow. These first 2 start with enols. This one started with the keto. I need you to know the mechanism for starting with either one. So if you start with a ketone, you need either an acid or a base to catalyze the reaction of keto-enol Tautomerization. And so here we had an acid and here we had a base. Here, gosh, I don't know what, we didn't have anything. So either one would work. Maybe breathe on a little bit, have a little water that could then dissociate, give you either an acid or a base. You have to look at some impurities to see where the acid or the base is. But nature's gonna make that happen. She wants her aromatic ring back. Here's the mechanism if it's acid catalyzed. Start with the ketone. Where are we headed? Well, if we start with the keto group, the ketone group, we're heading to enol, where the oxygen needs a hydrogen. That's the first step of the acid catalyzed mechanism. Go give oxygen its hydrogen. Did I do that right? I always mess this up. Well, this is my check. I think I did mess it up. No, we're good. Okay, second step. Let's make the double bond. Well, it's right here, so I want to put it there. That's where I mess up. I always think about putting curved arrow on this pi bond moving down here, but it can't happen because this carbon's sp3 hybridized. There's 3 hydrogens here. So I can't simply just move this double bond down here because that'll give this N carbon 5 bonds. No, you gotta get rid of one of the hydrogens to make room for the double bond. So water is gonna pick off that hydrogen, and then these electrons that hold the hydrogen place, they formed a double bond. So there's the alkene part of my enol. And then when this double bond forms, hey, this carbon can't have 5 bonds, so it bumps up the pi bond. And the water, the weak base, removing that hydrogen, reforms hydronium ion, and yay, we have a catalyst because you start with hydronium, you get it back. Let's squeeze it in over here. If you start with the enol, which is right here, yeah, why don't we just use that then? Okay. Poor play on my part, sorry. Okay, let's go the other direction. If you start with the enol and you want to tautomerize it back to the keto group with an acid, this is where I sometimes screw up. Sometimes I want to start off the same way I did here. Use a lone pair and grab another H, but they'll put 2 hydrogens on the oxygen. And what do we want? We want the keto group, which has no hydrogens on the oxygen. So don't think about moving the hydrogen first when you start with the enol. Think about moving the pi bond here. So it means you need to get rid of this. You can't just move it over here because that'd be too many bonds to carbon. I give it, yeah, no, it wouldn't. Anyways, don't try to put another hydrogen on here. Think about moving the pi bond. You bring down the lone pair to create the pi bond, and that bumps up, well, it kind of pushes this alkene pi bond to go grab a hydrogen because this carbon currently has 2 hydrogens and we need it to have 3. So in the first step of the enol tautomerization, starting with enol, acid catalyzed, lone pair comes down and pushes this pi bond to become a nucleophile. Go grab an H+. Not a nucleophile, sorry, to be a base. So lone pair oxygen came down to make the double bond. Ooh, that's looking closer to the keto group. And then this carbon grabbed a hydrogen. I guess I'll draw it in there. If you want to put in the other 2, you can, if that's helpful. And then hydronium becomes a water molecule. Oh, positive charge on this 3 bonded oxygen. And then the last step is, hey, let's reform the catalyst and get rid of that hydrogen and make the keto group. There we go. I like the base catalyzed mechanism better. For some reason, it sticks more clearly in my head. Let's start with the ketone group. Add in hydroxide ion or some other base. Give me a lone pair on that base. And it's not going to attack the lone pairs on this oxygen. Maybe that's why it's easier for me to remember. It has to find an H+ for this base, and that's over here. So go grab that hydrogen. Hey, these bonding electrons become the pi bond of the alkene, of the enol, bumps out the pi bond. Negative charge on that oxygen. We got a double bond here, and we made water. Before I continue or finish the mechanism, here. This is the enol. And if it loses a hydrogen, it becomes the anion of the enol. It's called an enolate. And it's resonance stabilized. Right? That's the whole driving force for why this hydrogen is weakly acidic. The alpha hydrogen is weakly acidic because it forms an enolate ion that's resonance stabilized. And we talked about how this form is more stable than this form because the negatively charged oxygen is more electronegative than negatively charged carbon. So this is more stable, the more stable resonance structure. So we got a name for it. It's an enolate ion or just an enolate. Okay, finish the mechanism. Well, we need to reform hydroxide from water. We need to put a hydrogen on the enol, make it an alcohol, the ol ending part. So hey, base, negatively charged oxygen, go grab a hydrogen from that water molecule. And then we have our enolate. And we recover our catalyst. Starting here with the enol and going to the keto group, probably down here is where I'll put it. Hey, base, go find an H+. Oh, well, here's a hydrogen. Why don't I take that one? Good for you, because that's what you're supposed to do. So hydroxide, remove the hydrogen. We have negatively charged oxygen. Hey, we're trying to form the keto group. So maybe if we draw, it'll help us figure out what we're supposed to do next. Oh yeah, I need to move this pi bond. But don't curve over it here. No, drop down a lone pair and kick this bond out to go find a third hydrogen for this carbon over here. Whoa, not what I want to do. Oh, I hit it over here. There we go. Technical difficulties. Okay, so lone pair, come down and form the pi bond. Alkene pi bond, go grab an H+. And then water, you are now hydroxide ion. And we're done. We formed a keto group. One more bit about acids and bases. The keto-enol equilibrium is affected by your choice of base. So I'm kind of hinting back at this, right? So here's equilibrium. Hey, the keto form, 99% here. Phenol, 99% enol form. And then this one, this enol is predominating. It's more favored than the keto form. Hey, how do we know which one's which? pK values. How can we adjust it to what we want? Like, do you want the keto form more often, or do you want the enol form more often? You can choose your base to make it work. So here's how it works. This will be useful in our next video. So keep this in mind, or review this part of the video when you're looking at the second video of Unit 4. But let's draw in, let's just use acetone and throw in sodium hydroxide. So is this going to be a favorable reaction? Does it want to go, or is this not going to work? Is sodium hydroxide too weak? Well, you can look at the pK values. We talked about it earlier. I know it's kind of confusing, so let's just quickly look at it again. Where is it? What a mess. Okay, here's water with a pK of 15.74. here's a ketone, pK of 19. So who's the stronger acid? pK is like pH. Smaller pH, stronger acid. Smaller pKa, stronger acid. Yeah, 1574 is a stronger acid than the ketone. Okay, if you switch it and you compare the bases, who's stronger base now? Well, the stronger acid gives you the weaker base. So hydroxide ion is the weaker base than the conjugate base of the ketone. Okay, so that says hydroxide ion is too weak. To get this equilibrium to favor, the hydroxide ion is too weak to remove that hydrogen. So I'm actually trying to do something that's not favorable here. Hydroxide ion is too weak to make the anion, but you can set up the equilibrium. It's going to favor the starting materials and not favor the product. That's supposed to be an arrow here. So remember doing that in general chemistry? Some of you guys are cringing. It's like, no, please don't do an ice table. Okay, I won't do an ice table. But anyways, here's the hydroxide ion. It's going to pull off this hydrogen, make the enolate, make a water molecule. I think that's all I wanted to draw. Where's the sodium ion if you're balancing this equation? It hangs out with whoever's negative. There's our enolate. Okay, and what I want to say is the keto is favored. If we're using sodium hydroxide. But if we stay with the acetone, same keto group, and we bring in LDA, that lithium diisopropylamide, diisopropyl, two isopropyl groups, double lone pair on nitrogen, it's negative, positive. Okay, so lone pair, go grab that hydrogen, make the enolate, same way, make that longer arrow, because now this stronger base, right? Who's stronger? Hydroxide ion or LDA? Order of basicity video. First rule of thumb is who holds a negative charge? Oxygen here, nitrogen here. Ooh, nitrogen, you're not very electronegative. It's not very happy. It's a stronger, more reactive base. LDA is a much stronger base than LDA. I'm sorry, LDA, much stronger base than sodium hydroxide. Negative nitrogen. So now the equilibrium favors the product side. So I'm gonna put a little arrow going backwards because the products are favored. So what are we doing here? Nitrogen grabbed this hydrogen, made the ketone, sorry, the alkene, the ene form, bumped this up, and now we have the enolate once again. And then we have the amine, diisopropylamine. Okay, where'd the lithium go? It's positive. It's a spectator ion. It's just following the charge. The lithium's up there. Doesn't matter if this is sodium, this is lithium. Does not matter. These are both the same base strength. They're the same functional group. They're both enolates. They're the exact same enolates. They have the exact same reactivity. But using the stronger base creates more of this. The enol is favored with the LDA. So we're using a much stronger base to force equilibrium to the product side and make the enol. So chemistry majors, hey, I'm talking to you guys. If you move on, you'll take some advanced organic chemistry. You'll see some other chemistry too, where this gives you control. You can actually say, hey, in my acetone solution, do I want a few of them forming enolates? Or do I want them all to turn into enolates? And that'll give you some control and some reactions. Actually, we're going to see that in the next video. So we'll come back to this idea. Good, enough about that. Let's see some reactions. Okay, so unit 4, you can either go by the broad category of carbonyl alpha-Substitution reactions. Yeah, we're going to pull off the alpha hydrogen and substitute that hydrogen with another group. The alpha hydrogen is being weakly acidic because it can form an enolate. And what we're going to substitute, we're going to put an alkyl group on there. So this whole this whole half of a unit goes by two names, Carbonyl alpha-Substitution or alkylation of enolates. It's saying the same thing. Okay, some general comments. There's going to be 3 subcategories. We're going to cover 2 of them in this video. Malonic ester synthesis is the first one. Okay, of these 3 categories, what are some common things, right? So these are kind of crazy reactions. Let's help us get through this. General things to be aware of. They actually contain 2 or more reactions that we've seen before. Okay, that's comforting. It'll look a little weird at the beginning, but we'll say, wait a second, these reactions remind us of something else. They'll help us get through them. One of those familiar reactions is going to be an Sn2 reaction. Substitution, that's the S part. Cool. The N part of Sn2 is nucleophile. There's also N and enolate, but it turns out the enolate has a lone pair, therefore is a nucleophile. And that's really the key here to understanding enolate chemistry. It's just thinking of it as a big, bulky nucleophile. And just go back to being comfortable with Sn2 reactions. And just draw the decorations that are around the enolate. The reactions happening at the alpha carbon, the one bearing the alpha hydrogen, which will then leave to form a nucleophile, a carbon with a lone pair. Cool. Ooh, but here's a good point to remember. What do we remember by Sn2? They react with primary, secondary, and tertiary halides? No. Sn2 doesn't like crowding, so it doesn't work for tertiary halides. Well, these enolates are going to be bulky already. So they're actually going to be so crowded that even secondary halides don't work very well. So that's something that you need to keep in mind. When you're doing these 3 subcategories of reactions in Unit 4, they are Sn2 reactions, but generally we can't use secondary halides. We did before. Sn2 worked fine for secondary, especially with a polar aprotic solvent like DMF, DMSO. Yeah, so that's not the case today. It's going to be a little different. All right, so what are we up against? Let's see the first subcategory. This one's called the Malonic Ester Synthesis. So you start with a malonic ester, and the structure of malonic ester, well, this is a common name. Looks like this. This is a malonic ester. The way they can differ is you don't have to have ethyl groups, right? So here's another malonic ester. This one has methyl. Doesn't have to be methyl. It could be isopropyl. Could be a tert-butyl group. It could be lots of things out here, but that's how it varies. But to be malonic ester, you always have 3 carbons that are esters. There you go. The IUPAC name, right? This would be diethyl propanoate, propane dioate. Where's my cheat sheet, my notes? Yes. I'm not going to ask you to name it, but for those of you who care, diethyl propane dioate. I'll put in parentheses because you don't have to know that, but there you go. Maybe you want a 1,3 in front of this, in front of the dioate, but not required. Those are the only, carbon 1 and 3 is the only place you can put the ester group. Okay, so we actually have 3 reactions. That was one of the ideas we had about these subcategories of reactions. They're actually, even though we call it by one name, it actually consists of 3 reactions. First, you're going to add a base that matches the ester. More on that in a second. We're going to attack the alpha hydrogen with a base. Second, we're going to do the Sn2 reaction. So you add a methyl or a primary halide. Can't use secondary, definitely can't use tertiary because we're doing the Sn2 reaction. Third, we're going to add some hydronium ion, dilute acid. That's going to cause a third reaction, hydrolysis of esters. We saw that in our last unit, Unit 3. And then there's a fourth reaction. We're going to heat this up at the same time we're adding acid. We're going to get something new called the decarboxylation reaction. So we actually have 4 reactions here. And it's all going by the name Malonic Ester Synthesis. I know, so one step at a time. That's a lot to handle, but if you break it down and just think of it in chunks, it's easier to remember, easier to understand. So chunk number 1, acid-base reaction. Let's pull off the alpha hydrogen. So here's our double bond O. Next door is the alpha carbon. Let's remove that hydrogen. And we need a base. Sodium hydroxide? No, that's not very strong. Instead, you need one that matches the ester. So right here, we have an O with an ethyl. So we have to use an O with an ethyl as a base. Maybe sodium. That's our base. And we usually use the same structure as a solvent. So sometimes you'll see this listed as a solvent. Hey, chem majors, if you want to create this base, what you should do is you go to the stockroom, get some ethanol, that's a solvent, and add a chunk of sodium metal. And then some of the alcohol molecules react to sodium metal to form the base. So it's really easy to prepare this basic solution. Then you add your malonic ester and you remove the alpha hydrogen. So that's a negative charge. Actually, I like to put it here. Kind of looks like a smiley face. Anyways, that's your enolate ion. The alpha hydrogen has been removed. That's step 1. Step 2 is now, hey, this is a nucleophile. Somebody's got a lone pair. Why don't you attack a primary or a methyl halide and do an SN2 reaction? So I'm not going to draw the curved arrows, but you know it. It's SN2. Lone pair hits this carbon, bumps out the halide. And put a methyl group right where the lone pair used to be. Optional. If you want to do 5 steps, base, SN2, hey, there's still alpha hydrogen here. You can do it again. So this is optional. Step 1, add a base, remove the hydrogen. Step 2, add a primary or methyl halide. And it doesn't have to be the methyl halide used before, it could be something else. So I don't know. Why don't we use 1-bromoethane? And so now the lone pair, after hydrogen is removed, lone pair will bump out this halide. And now we've actually substituted both alpha hydrogens. First time with a methyl, second time with an ethyl. And I know this molecule is getting kind of crazy decorations, but focus on the alpha carbon and just ignore the other groups for the time being. Makes it easier. Step 3, we're going to add hydronium ion and heat. Add hydronium ion and heat. Okay, the hydronium ion is going to attack the esters. So go back to unit 3, look at ester hydrolysis. Esters are hydrolyzed to carboxylic acids and alcohols. So right here where the alcohol, sorry, right here where the ester is, there's 2 esters. They both react. So this one cuts here. Hydrolysis means cutting with water. Hydronium ion, acid catalyzed hydrolysis with water. We cut that to form this alcohol. And then this part is a carboxylic acid. So we're focusing on this side of the molecule. We got the products. And then this carbonyl carbon connects to the methyl group, which connects to the other carbonyl. And now we cut over here. Hydrolyze this ester to again make a carboxylic acid. And then this piece is the alcohol. I'm going to put this in parentheses because on the exam you don't have to draw those parts. Actually, you don't have to draw this part either because this intermediate reacts with heat and it does a new reaction we'll talk about separately in a few minutes called decarboxylation. Decarboxylation. What the heck does that mean? D means to detach, remove, detach, what? A carboxyl group. Yeah, a carboxylic acid group. So you pick one of those, just leaves. You take your carbon, the two O's, and you leave as carbon dioxide, and the hydrogen stays behind onto the alpha hydrogen. So the final product, let's see, if I choose this one to leave, then the left-hand side stays. But I could have drawn, like I said, well, the left-hand carboxylic acid could be the one that leaves and keep the right one. Same molecule, do it down here. Acid hydrolysis clips off the esters, heat decarboxylates, removes one of the carboxylic acids. So maybe I'll keep the right one this time. So I've drawn the right-hand piece, the carboxylic acid. This is the one that remains, and you still connect to a methyl, and you still connect to an ethyl. And then, yeah, this becomes carbon dioxide. The alcohol group, I'm not writing in there. There we go. That's the Malonic Ester Synthesis. Lots going down. Let's see. I got a few notes here. Let's see if I missed anything. Let's see. A primary methyl alkyl halide, steps 1 and 2 can be repeated. That's our optional step. We did repeat it with the base and with the alkyl halide. Melanate's a common name for 1,3-propane dioate. Oh, yeah. Overall, ooh. So this is change of perspective. Okay, get everything on the screen. No, it's off the screen. All right. Let's redraw it. Let's draw this molecule over here. Okay, overall, you take an alkyl halide, the alkyl halide changes into RCH3OH. So if I say, hey, methyl, you're just the remainder of the molecule, the product after Malonic ester synthesis takes over is that you get a CH2 group plus a carboxylic acid. Or in other words, the methyl group has a CH2 group and a carboxylic acid. Get it in there. Okay, so I don't know how helpful that is, but that's the pattern, focusing on this reagent. You start here and you add this group on. If you do it 2 times, well, then you start with this R group and you add a second R group and you get this over here, kind of the same pattern. And yes, there's a mechanism. Thankfully, though, the only one that's new is this decarboxylation. You guys have drawn, gosh, it was like back in first semester organic chemistry, we've seen the mechanism for acid-base reactions. Oh my goodness, we've done SN2 reactions all the time. It wasn't too long ago we were making ethers by an SN2 reaction. We had to draw the mechanism there. Last unit, we hydrolyzed esters, showed the mechanism there. So we already know 3/4 of the mechanism for this crazy Malonic ester synthesis. The only one to add is decarboxylation, and it's only 1 step. Beautiful. But it's really lengthy when you put them all together. But that's how you got to do it. You got to do it in chunks. There's four parts. Just do it in chunks. Let me check my notes before I jump in on the mechanism, because it's going to take a few minutes to go through 4 mechanisms. Am I missing anything? Yes. One more detail before we jump into the mechanism. This little notion about the base matching the ester. I got a little assignment later, not this associated with this video, to kind of give us a better understanding of why. But right now, it's a general rule. Your base, the base you pick, it's not going to be sodium hydroxide. It's not going to be LDA. You have to choose the one that matches the ester. So if you have ethyl groups at the end of malonic ester, you have to have an ethyl group on oxygen. If you choose this one, where there's methyl, well, then your base has to match the ester. This methyl with an O, that's the form of your base. And if you want to put an Na there, you can. Or you just draw that. I'm fine with that too. If you had isopropyl, sorry, am I beating this dead horse? What's the expression? I don't know. But I'm gonna do it anyways. Base has to match the ester. Here's my ester, that's my base. Which is kind of cool actually, because on the exam, I have to give you this and ask for either the reagents or the product. So you look at the structure and you already know the first reagent. The base matches the ester. Let's look at the mechanism. You might want to pause it, stretch a little bit, get a drink of water. Jump right in, let's do this. All right, let's find some shortcuts. First shortcut, this Malonic ester is big. I'm tired of drawing it. So most people don't. They abbreviate it. The alpha carbon is the most important part. Then what the heck is this? It's a C with 2 O's. What's this? That's an ethyl group. So sometimes you see ET. If it was methyl, you'd see an ME. Me. And then there's 2 of them. There's the same thing on the other side. Sometimes you see it drawn like this. Sometimes you'll see it. Oh, no, I guess it's backwards. Sometimes you see it like this. Okay, lots of shortcuts. You pick the one that works for you. All 4 of these, totally acceptable. Where are my notes? Make sure I didn't forget another one. Now, we're good. All right, let's go with this skeletal drawing though. Okay, so step 1. What are we doing in Malonic Ester Synthesis? We're attacking the alpha hydrogen with a base that matches the ester. You can do that, right? If I'm matching my ester, it's got an ethyl group, or you could draw it like this. Don't give me both, sorry. And we're doing mechanism. Let's clean up this whole screen. Some of you like taking screenshots at the end. Man, this is messy. Let's clean it up. Also, I hand wrote very carefully the mechanism, and I attached it as a separate document on Canvas. So I have the mechanism all mapped out very neatly for you. It's 2 pages. Some of you, though, I think will appreciate going through the mechanism step by step. So let's do that. Okay, step 1, go attack an alpha hydrogen. So let's put one in there. There it is, right next door to the carbonyl group. Remove that and do a little U-turn. These bonding electrons become a lone pair on the carbon. What is wrong with my pen? What is wrong with me, my hand? Okay, make a little smiley. Oh, that's not too happy. There's my, that's just a single bond. There we go. There's my enolate. Step 1's done. I made the enolate, the weakly acidic hydrogen, alpha hydrogen, it's gone. Let's do an SN2 reaction. So I can only use primary or methyl halides. Well, how about if I use a methyl halide? Nothing special about bromine. It's my favorite, but chlorine works too. Tosylate, iodide, 2 curved arrows in your SN2 reaction. This one is an acid base. I should have stated that. That's how you kind of remember this in chunks. Base matches the ester. Start with an acid base reaction. Set it up with an SN2. We got a good nucleophile here. Bulky nucleophile. That's why you can't use secondary halides. Definitely can't use tertiary. Okay, at the end of SN2, 1 step, 2 curved arrows, just like all SN2s. We have our methyl group here. Step 3, hydrolysis. Twice, because there's 2 esters. Yeah. We can do this. Just do it in chunks. Go back to Unit 3, watch that video game. It'll say, hey, when we hydrolyze esters, I'm going to pick the right one to go first. The lone pair on the carbonyl oxygen grabs an H+. Then the weak nucleophile bumps up the pi bond. I'm trying to hydrolyze this to make a carboxylic acid. So I want the pi bond back. I want this to be an OH group. This group needs to leave, and it can't leave now, it'd be negative. And this is acid catalyze. Acid catalyst means only plus ions, cations, and neutral compounds, no negative charges. So hey, I need to get rid of one of these H's. Why don't you take it? Cool. Okay, bring down my pi bond. Let's make that carboxylic acid, or at least get closer to it. And we hydrolyze. We actually cut that bond, cutting with water. I'll swing this OH group out to the side, and then I'll sneak in the alcohol group that got cut off. And then we bring in another water molecule. I'll put it up here. And that acts as a base, and yay, arrow, we have finished hydrolyzing the first ester. We got our carboxylic acid, but there's another ester. Ooh, don't lose the methyl group, Dennis. Darn it, I lost it a long time ago. Okay, that's a 2 reaction, put a methyl group here. Sorry, I know some of you watched that, it was bugging you. There we go. Okay. Now we have to do it again. This video is getting way too long. So I'm going to pause the recording, put all the steps in here. And if you don't know what they are, rewind it because it's going to be exactly what we did up here. Let's give myself some room. Come on. Okay, so everything's on the screen now. We start with this ester, add hydronium ion, we hydrolyze it again. Same exact mechanism. And yes, if you choose, right, so on my exams, I'm going to give you the option of choosing which molecule you want, or which reaction to show the mechanism for. If you choose the Malonic Ester Synthesis mechanism, yes, you have to show me both esters being hydrolyzed. Okay, we're not done yet. We still have to decarboxylate. So the last part of the Malonic Ester Synthesis is to add heat. And all it does is a Diels-Alder-like reaction, or a Claisen rearrangement type reaction. Remember, it's one step and 3 curved arrows trying to make a benzene ring, but it doesn't. So what I like to do is redraw this so it looks more like a benzene ring. So what am I talking about? So review the Diels-Alder reaction. Remember, that's where you have a conjugated diene, and you bring in another alkene or an alkyne, and you try and make it look like benzene. So if we could close this gap and that gap, it would be benzene. So hey, pi bonds, use your electrons to close this gap, push this way, go this way, and close that way. Follow the arrows, excuse me, to see what happened, and we lose 2 of the 3 pi bonds. So we don't make benzene. Instead, we made this bond, we make that bond, and then this pi bond goes over here. We actually make cyclohexene. So we're going to do that here again. So this is sort of looking like where my hexagon could be. And I got a pi bond here. Well, there's a second one there, but wait, it's not in the right place. So you kind of have to, it doesn't work. You need to spin this bond, or in other words, instead of the double bond O pointing up, alcohol to the bottom right, switch those positions. So start drawing the other side. Okay, so the double bond O is currently up. Let's put the alcohol group up. And I want a hexagon, so I need a 6 atom over here. That's going to be hydrogen. And the double bond O, that's off to the side. Hey, where have we seen this structure before? Right over here. Right here. The enol form. When you have a diketo compound, diketone compound, the enolate is actually favored, where one of the ketones goes to the enol form and you can get internal hydrogen bonding. So that's what we're doing here. More space. Okay, so now that's what you have to do. Get this internal hydrogen bonding. Don't put it in the dotted line, but hey, there's our gap. So that's what we want to do is the nearest pi bond, close that gap. Nearest pi bond, oh, that's this one. So pi bond, you go here. And then we're going to do 3 arrows. So I'm starting to go clockwise. I got 1 arrow there. Next bond goes here. And this one goes there. And I know it's a little frustrating that in Diels-Alder, you're moving pi bonds. And in here, you only have 1 pi bond. You have to move 2, what are these called? Sigma bonds, single bonds. We kind of saw that in the Claisen rearrangement too. We had to do the same thing. We didn't move only pi bonds, but it's the same pattern. 3 arrows going around within a hexagon. Okay, and what took place? Well, let's follow arrows and mark the changes. This bond, no change, so it's still there. This bond, well, it was a double, but the pi bond left, so now it's a single. What's this arrow says? The pi bond moved there. Hydrogen, you stay put. This bond, no, it's gone. It formed a double bond over here with the oxygen. Anything happening in this double bond? No, there's no arrows here, so that's still there. This bond, though, it's over here. It's a double bond there. And the methyl group, it's fine. Yeah, that's the next thing. Hey, what the heck is this? There's a carbon here with 2 oxygens. That's carbon dioxide. Yes, this decarboxylation reaction, that's the name of this last step of the mechanism of malonic ester synthesis. It's where you have a dicarboxylic acid positioned this way. You have 1 carboxylic acid and 2 carbons away. On the beta carbon, you have a 2nd carboxylic acid. You heat it up and they're unstable. They kick out a carbon dioxide molecule. Probably because it has 2 carbonyl groups that nature likes. It's really stable. Carbon dioxide is a very stable molecule. And what's left over, well, let's rewrite it. I'm going to put this molecule, I'll put both of these down here. I'm going to get rid of this bond, just write OH. I got a double bond there and a methyl here. Hey, that's an enol. And for most enols and ketones, the keto group is the favored one. And actually, we want a carboxylic acid back. So yes, we do want this to be a double bond O, a carbonyl group. We have to tautomerize it. Okay, and there's the product, carbon dioxide. Okay, so what are we going to do? Well, to get enol to tautomerize the keto, we need a catalyst, an acid or a base. So what do we have? Do we have an acid or a base here? We have an acid. So we added the hydronium ion at the same time we heated. So we added an excess of acid. Okay, so what's our goal here? We want to make a ketone. So I need a double bond here. I need this pi bond to leave, and I need to move this hydrogen. So I'm bringing in the H. Don't put an H up here. You want to get rid of this hydrogen. Oh, that's right. Over here, there's only 1 hydrogen present. And if I get rid of this, make this a single bond, I need another hydrogen here. So the first step, going from eno to keto, is lone pair, form a double bond. Oh yes, I want that. This alkene pi bond, go grab the extra hydrogen that you need at the end of this carbon. Okay, so what do? We got this alcohol group on the side. We formed a new double bond O. Ooh, and the hydrogen's still here. 3 bonds of oxygen. Single bond forms here. Still got the methyl. And then I guess I'll put in, well, this hydrogen's drawn in already, and I might as well draw in the new hydrogen I put in there. Carbon dioxide, you can bubble away and leave. The hydronium ion forms water. This needs to be a carboxylic acid or the keto group. Lone pair on the water, go grab that H+, and we're done. Finally, Malonic Ester Synthesis. Phew. And that's the world record in organic chemistry. Yeah, that's as long as a mechanism as you'll ever see in this class. There are none longer. There's another one that's going to try and be just long. Okay, rewind that. Kind of break it down the parts, and then, yeah, definitely do it in parts so you can understand it. Okay, anything else on this side? I think we're good. It's time to look at decarboxylation and wrap up this video. Okay, decarboxylation does not occur only in malonic ester synthesis. It's actually an independent reaction, and it happens anytime you have a carboxylic acid. I mean, if it's going to decarboxylate, you need the carboxyl group, the carboxylic acid group. And what makes the carboxylic acid leave is 2 carbons away. On the beta carbon, you have to have a carbonyl, a keto group. Okay, so here's probably the classic example. Here's my carboxylic acid, beta carbon, there's a ketone. Sweet, this molecule can decarboxylate. What about this one? No, the ketone's on the alpha carbon. It needs to be on the beta. It's not beta, you can't decarboxylate this. This one doesn't react. Nor does this one, right? The ketone's on the gamma carbon, not on the beta. It has to be beta. Yep, okay. But let's go back here. It's a keto group, which is a nickname for carbon-oxygen double bond. Doesn't have to be ketone. So here on the beta carbon, so carboxylic acid, most important group, beats out amides. Carboxylic acid's top of the ranking list of functional groups. Beta carbon has a double bond O group. Yeah, it belongs to the amide, but who cares? Nature doesn't. Double bond O means that she can decarboxylate this, heat it up, and it falls off right here. And then this will be, well, this carbon's still there. Yep, the carbon's still there. Right now, this carbon, if you get out of skeletal drawing, there's 2 H's, but this hydrogen migrates over for 3 of them. And of course, you decarboxylate, make carbon dioxide. Got an ester here, carboxylic acid, alpha, beta, nothing here, but beta over here. Yes, there's a keto group. I know it belongs to the ester, but you can still decarboxylate. Got the amide next to carboxylic acid. Oh, I did this just so, right? Get used to the fact that when it's drawn, it doesn't always have to have carboxylic acid on the right side. Carboxylic acid might be on the left side, alpha, beta. Hey, here's the keto group. This one decarboxylates. Here's an aldehyde, yeah, a keto group. Good. This one gets a little trickier because there's a bunch of double bond O's. So first, find the carboxylic acid, then the beta carbon. Nope. This one can't decarboxylate. Let's see, which one did? Let's do this one. Okay, so I'm gonna take this molecule and show the mechanism. What you have to do is get in that keto-enol form where you get the 6-member ring going. So instead of the double bond O being here, you want the alcohol and show that bond so that now I see my hexagon. And so I didn't put double bond up, I put double bond up to the side. The mechanism of decarboxylation is close up the gap. So move the pi bond into there, and then 2 more arrows to move these single bonds around the ring, this imaginary hexagon ring, and then follow arrows and make the changes. So this hexagon didn't change, but there's an arrow here. Hey, so this bond became a double bond there. And then the double bond, well, the pi bond left, So I only have a single bond, and that bond connected to the hydrogen. On the other side of hydrogen, hey, hydrogen can only make one bond. It's made its bond. So this bond had to move and made a double bond here. Double bond O, that's carbon dioxide. Yep. And then, if we're following the mechanism, let's just assume it's acid catalyzed. Oh, because it has a carboxylic acid here. So that helps. There'll probably be some contaminated water here. I think we're just going to assume there's a little hydronium ion, a little acid catalyst, so that, hey, lone pair, come down, go grab the H plus with my curved arrow. That's a weird curved arrow. This pi bond grabbed the H plus, hydronium became water. Scroll down, give me some more room. And then, hey, water, you be the base, grab that H, make my final product, my keto form, double bond O, but it happens to be a ester. Huh, and we're done. There you go, decarboxylation. Hey, you want to do a chemical demonstration? Let's do a decarboxylation together. Take a deep breath in and let it out. What's one of the gases we're emitting? Carbon dioxide. Yes, in metabolism, in our bodies right now, the breakdown of glucose, one of the steps in metabolism is a decarboxylation step, and it produces carbon dioxide, which is a waste product for us. Cool. Okay, more loose ends to kind of tie together before we shut down this video. Here's ethyl melanate again, a malonic ester. And we added the base. Hey, it matches the ester. 2 carbons O, 2 carbons O. That's step 1. Little step 2, we have a dihalide here. Okay, so add the base, make the nucleophile, the enolate, and then it can attack one of these. So maybe I'll attack this one. And this will be your product. But then you got a base again. There's still hydrogen here that can form the enolate nucleophile. And then now you have to think about three-dimensionally, maybe building a model and wiggle this so you can get the bromine to be 180 degrees away to allow this SN2 reaction to go. And you can close up the ring. Isn't that cool? So now we have a new way of making rings through Malonic Ester Synthesis. And of course, then you hydrolyze the esters, cut these off. I guess I cut them off right there. Make them carboxylic acids, and then you heat it, decarboxylate, and then that's your product. Pretty fancy chemistry we got going on here. All right, that's the first subcategory of alkylation of enolate ions or carbonyl alpha-Substitution reactions. The second category, Dennis, what are you doing? Second category, yes, we're going to start it, is acetoacetic ester synthesis. It's the Malonic ester synthesis. It's exactly the same. You just start with a different molecule. I got all these notes. They're exactly the same. So Malonic ester synthesis, that's the one we took the most time on. That's the one that we got all the video about. But the acetoacetic ester is where you take one of these esters, I'll choose the left one, and you make it a ketone. And I picked methyl. You don't have to. It could be an ethyl. Doesn't have to. It could be a benzene ring out there and then the ketone or whatever. The point is, the acetoacetic ester synthesis is much more useful. Hope that didn't show up in the recording. Probably did. Much more useful than the Malonic ester synthesis because you have so much variety out here. But it's exactly the same. Let's pick this one. This one is acetoacetic ester. That's the parent here. We got, acetoacetic ester is the common name. What do? Malonic ester synthesis, but with this, with the ketone and an ester. Step one, choose a base that matches the ester. Well, I chose ethyl, so gotta keep my ethyl group going. What's this base doing? It's pulling off the alpha hydrogen. But isn't there an alpha hydrogen over here? Yes, yes there is. Next door to the keto group, there's a hydrogen, it's weakly acidic, but you only get one, or you only get one pair of resonance structures. These hydrogens, there's two of them there. This hydrogen, one of these two hydrogens is much more acidic because then you get more resonance structures. So you only form your enolate here. Step two is Sn2. So pick some methyl or primary halide. You can do it twice since there's two of them there. And then what you do next, you heat it and you hydrolyze it. I guess you hydrolyze first and you heat it first. And now you have to be careful. There's only one ester. So there's not an ester on this side. So now all of us are going to hydrolyze the one and only ester here, hydrolyze it, but then you decarboxylate it. You lose a carbon dioxide molecule. So your final product is this. Well, it looks very similar to the Malonic Ester Synthesis, except you didn't have a carboxylic acid over here. You got a ketone. And whatever group you start out with is what you end up with, is still there. So I start with methyl here. I got methyl there. If I had the benzene with the methyl, I would have a benzene with the methyl here. Exact same thing. Exactly. So I'm not even going to repeat the mechanism because you got it already. Yay. Okay. Whew, heavy, deep breath. I don't think, fingers crossed, we'll ever have another video as long as this one. Thank you for sticking around. I'll see you in the next one. Take care.